Hello, this is Nicholas from Silicon Chip, and today I'd like to talk about this article we have coming up in our February issue, which goes on sale in late January 2026, about the mains hum notch filter. So this is a circuit that takes an audio signal and removes a very narrow range of frequencies, either centered around 50 hertz or 60 hertz, depending on what the mains frequency is where you live. And the idea is that if you have an audio signal that has mains hum or buzz or pickup in it, and you can't get rid of it, this will remove it. And it does it by simply removing those frequencies from the sound. It's a sort of a last resort because there are better ways to get rid of mains pickup. One of them is to use balanced audio leads, but there are times where you can't. You might have audio leads that you can't change. They're in a wall, in a conduit, you can't access, something like that. Or you've tried everything and you simply can't get rid of that sound, and the solution is the notch filter. So you can see here it's in a small plastic instrument case. It runs off DC power, and you just feed the signal in. It comes out, can go to an amplifier, something like that, without the mains signals in it. And we have a kit that has the board and the parts that go on it. So for people who don't want to have to gather the parts themselves. So let's have a look at how it works. Here's the frequency response of the prototype that we measured. And you can see how the frequency response is pretty much flat over the audio range except for just around 50 hertz, which is our local mains frequency. And those frequencies have been essentially removed from the signal. And here's a close-up of it. You can see that basically only frequencies from about 48 to 52 hertz are affected. Everything else is pretty much left alone. And here's a plot of the distortion, which shows that there really isn't much distortion introduced to the audio signal, except of course around 50 hertz as you'd expect, because it's modifying the signal there. So with something the 2 volts RMS you'd get from something like a CD, DVD, Blu-ray player, it's very low down. It's around 0.005% distortion, so probably not audible. And then here's our circuit diagram, which is relatively straightforward. It uses very standard TL074 op amps. It uses that's a quad, and I believe there are 2 quad op amps. There's also a single TL071 that's used for the half supply generator. So because it's DC powered, we need to bias the signal. Say your DC supply is 12 volts. You want to bias the signal to about 6 volts DC so that it can be handled, processed by these op amps, and that's what this circuit snippet here does. It generates a 6-volt rail, buffers it, and then biases the incoming signal to that. And then at the end, after it's been processed, it's biased back to 0 volts, so it swings symmetrically before it's fed to the outputs. We have read relays here at the outputs. These are used to disconnect the signal when the circuit is stabilizing. So basically the outputs are not active until a few seconds after you power it on. And then if you remove the power, you switch it off, the outputs are immediately disconnected so that you don't get thumps and things like that in the audio signal. And this 555 timer here is responsible for controlling that relay. But the main part of the circuit is this Flieg notch filter, which is built around this quad op amp. The nice thing about the Flieg filter is that you can adjust its frequency using a single resistance. So we have a trim pot here that could be used to fine tune the frequency, so it's very close to the desired notch frequency of 50 or 60 hertz. We also have another single trim pot for each channel here that adjusts the Q factor, so basically how deep and narrow the notch is. Probably don't want maximum Q, the reason being if the notch is too deep and narrow, because firstly because you might not have set it exactly at 50 or 60 hertz, but also because the mains frequency can vary slightly over the day. It averages very accurately 50 or 60 hertz, but it might be 50.1 or 49.9 at certain times. So you still want the notch to be effective then. So you want it to be a fraction of a hertz wide. So we have some guidance on how deep to adjust the notch, but of course it's up to you. You can adjust it. And there's also 2 further trim pots here. These are optional. So this one and this one. So basically, if you have very precise, say 1% 47 nanofarad capacitors, you can use fixed resistors, 1% resistors, 1% capacitors. The notch will be close enough, and then you just use this fine frequency adjust to set the frequency. But 1% capacitors are very expensive and not easy to get. So more realistically, you'd use 5% capacitors, and then instead of having these 2 fixed resistors, you have this trim pot, same over here, and then you just adjust the trim pot to compensate for any variation in capacitor value to get the notch frequency correct. So signal comes in here through a ferrite bead for RF rejection, stopper resistor, coupled to this op amp, which is a buffer. The buffer drives the notch filter, so this is what removes the frequencies we don't want. And then it's coupled again to remove the DC bias, passes through the read relay, and then through this resistor for stability to the output. So a relatively straightforward circuit. It's not simple to see how the notch filter works, but it does. This configuration here of these 3 op amps per channel provides the notch that we need, adjusted by those trim pots, as I said. Here's the list of parts that are required. So a circuit board, the plastic enclosure it fits into neatly. You could put it in a different enclosure if you want, but it fits into this one. And then all the various connectors, relays, ICs, regulator, transistors, diodes, etc. So as I mentioned, we have a kit for this that comes with pretty much everything here. It doesn't include the case or a power supply, but it has the board and everything that mounts on it. Here's the overlay diagram that shows where the components go, how they're orientated, so on. It's a relatively simple build, all through hole parts. Everything is labeled here so you can see where to put it. But the only tricky part is basically verifying that your 47 nanofarad capacitors are close in value to each other, which is necessary for the notch to work properly. But we found that when you have 5% capacitors all from the same batch, they're usually very within 1% of each other. So even if they're not exactly 47 nanofarads, it doesn't matter. As long as they're close to each other in value, you can trim out the error using these trim pots. And that's what it's included in our kits. Our kits have the trim pots because 1% capacitors are just too expensive to really consider. So here we have some more information about if you want to remove higher mains harmonics, because when you get 50 hertz induced into your signal from the mains, you're usually also going to get 150 hertz, 250 hertz, and so on. Because this, if you can see from this scope grab here, the mains waveform is not a pure sine wave. It has some rounding. It's sort of like a combination of a sine wave and a square wave, and square waves have odd harmonics. So you could have 2 or 3 of these units if set to different frequencies if you wanted to remove the harmonics, if it was that important. So there's some information on how to do that, how to build multiple units that would work at different frequencies. Here are some photos of the finished unit, some panel drilling details. Pretty straightforward to drill the panels. Looks like 6 holes to be made. And you can see how the board just basically drops into the case and fits very neatly. So there you go. The notch filter is an easy board to build, solves a problem if you have that. And it's kind of an interesting circuit, I think. And surprising that it performs so well when it's just using TL074, very common cheap op amps. Despite that, we can get almost down to 0.001% distortion plus noise. So quite reasonable performance. That's the notch filter. As I mentioned, it's going to be in the February 2026 issue. It goes on sale late January. So look out for that. Silicon Chip magazine, available in news agents in Australia and New Zealand, and via subscription all over the world. Thank you. Have a good day.